Swayam Prabha. Digital India. Educated India.
In our last lecture, we have seen that an epicyclic gear train has 2 degrees of freedom, right? Epicyclic gear train because it has 2 degrees of freedom, it can create 2 output speeds from single input speed, and that has lot of application. For example, very commonly used epicyclic gear train for the same purpose, that it can create 2 output speed from 1 input speed, is in automobile differential. As we know that when an automobile goes in a straight path, both the rear wheels rotate at the same speed. But if the car wants to take a turn, then the input speed may not change, but the outer wheel must rotate faster than the inner wheel. That means from the same input speed, I now must create 2 different output speeds when the car wants to take a turn. And that is possible because the input shaft and the wheels are connected by what we call an automobile differential, which is nothing but an epicyclic gear train having 2 degrees of freedom. Let me draw the differential sketch. These are the 2 shafts to the wheels. This is, say, to the one of the rear wheels, and this shaft is the other, connected to the other rear wheel. These are bevel gears which are connected by another bevel gear. But this bevel gear is carried by an arm. So these are 2 bevel gears which are connected to the 2 rear wheels. This is another bevel gear which carries this arm. That means this bevel gear can rotate about this arm. There is a revolute pair here. That is what we call the planetary gear. And this bevel gear is driven by this bevel gear. This is the input. The input comes to this gear which drives this bevel gear. This bevel gear carries this arm and this bevel gear is carried on that arm. So there can be relative rotation between this arm and this bevel gear. This bevel gear connects these two bevel gears which are connected to the wheel. Let me say these gears we name 1, 2, then this 3, this is the arm which is same rigid body as this gear which is 4 and this is 5. So N5 is the input speed. This small n I refer to the RPM, we call it input speed. This N5 decides the rotation of 4, so N4 we can find that will be N5 by N4 into N5, where N5 and N4 are the number of teeth on these two gears. So depending on the direction of this rotation, we can find what is the direction of this rotation of 4. And 4 is nothing but the arm. To analyze this epicyclic gear train, what we do, we follow the same tabular method which I said earlier. We talk of condition and we are interested in gear number 1, gear number 2 and arm. This gear 1, gear 2 and arm or gear number 4, they are the same. So first we say everything is locked to the arm. All these elements are this gear, this gear, this gear, everything is locked to the arm. All elements locked to arm. And then the arm is given some y revolution. Because 1 and 2, 3, everything is locked to the arm, this whole thing rotates like a rigid body. So 1 and 2 also gets the same revolution y. Then we say the second condition. Second condition is we lock the arm. That means we hold this fixed. So arm is locked. So no revolution to the arm. Then these two gears are of same dimension, they have the same number of teeth, only if the arm is locked, this gear is rotated, the arm is not moving, so this is like a simple gear train. So this motion is transmitted to this gear to this bevel gear. And the number of teeth on this gear is unimportant because the intermediate gear, and because these two gears are of same size, only thing they rotate in opposite direction. So if gear is 1 is given x revolution, gear 2 gets minus x revolution. So the resultant is x plus y, y minus x and y. So what we see that if the arm rotates, we can say speed of 4 which is y is nothing but n1 plus n2 by 2. So whatever may be the values of x and y, it is the average of n1 plus n2, average of n1 and n2 will be the rotation of gear 4. When the car is moving in a straight path, there is no relative rotation between this gear 3 and the gear arm. There is no epicyclic action. This acts like a key. So N4 just drives N1 and N2 in the same speed, and this gear 3 does not rotate. This does not have any gearing action. This just acts like a solid connection. Then N1 is same as N2, is same as N4. So straight track, if the car is moving on a straight path, there is no relative rotation of gear 3 with respect to the arm. There is no epicyclic action. Gear 3 does not revolve about its own axis. Gear 3 acts as a key, and N4 is same as N1 is same as N2. Whereas if the car takes a turn, then this gear starts rotating about its own axis, and average of N1 and N2 becomes N4. So if it is x plus y and y minus x, their speeds are different. One is y plus x, other is y minus x. So this is how an automobile differential can create two different output speeds if necessary because of this epicyclic gear trend. We shall now solve one or two more problems to show you this tabular method for analyzing epicyclic gear trend. As I said, let me now solve this example of an epicyclic gear trend. This is an epicyclic gear trend where the input shaft 1 is connected to this compound gear 1 and 2. That is, the speed of this shaft is the same as that of speed of gear 1 and gear 2. Gear 1 is connected to this planet gear, gear 3. Gear 3 is carried by this arm. That means there is a revolute pair here. And this arm is this gear 5, which is an internal gear. This 5 is an internal gear, which is this arm for this planet gear 3. And the gear 3 is also connected to this internal gear 4, which is fixed. This internal gear 4 is not rotating. This gear 3 is rotating in space, moving in space the axis of this gear. As this gear rotates, the axis of this gear 3 is carried in space. Gear 2 is connected to this planet gear 6, which is carried by this arm. There is a revolute pair between the arm and gear 6 here, and gear 6 is also connected to this internal gear 5, which is rotating. Our objective is, if the number of teeth are specified, input speed is specified, we have to find the output speed. We have, for example, let's say the input speed is given to be in this direction 1000 RPM. What is the output speed? What is the second output speed? Because we are specifying one input speed, it is an epicyclic gear trend, so we must specify two input speeds. The other input speed is specified as this gear 4 is fixed. That is, speed of gear 4 is 0. So the other is speed of gear 4 is 0. So now two input speeds are specified, 0 and 1000 RPM. We have to find out this output speed, what is N2. So that is the question. Obviously, number of teeth on various gears have to be specified. Let me say number of teeth on gear 1 is given to be 20. And the number of tooth on gear 3 is 30. Number of teeth on gear 2 is 24. And number of teeth on gear 5 is 80. This is an intermediate gear. The number of teeth is not given and not necessary either. Here also number of teeth on gear 3, though it is given, is not necessary for any speed calculation, but you notice the number of teeth on gear 4, which will be necessary because that is not an intermediate gear. So that can be calculated from this value. That is what is number of teeth on gear 4 that we need for calculation of various speeds. Whereas here We can calculate the number of teeth on gear 6 from this 80 and 24, but we will never need it. So this is the problem. The epicyclic gear train is specified, 2 speeds are specified, 1000 and 0. We have to find out this output speed. Let me now solve this problem. To solve this problem, first of all, let us see that there are 2 epicyclic gear trains in this whole gear train. There are 2 epicyclic parts because there are 2 arms. One arm for this is the arm, which is nothing but gear 5, and for this portion this is the arm which is carrying gear 6, and this arm 5 is carrying gear 3. So let me first consider one epicyclic gear train consisting of gear 1, 3, 4 and its arm, which is nothing but gear 5. Number of teeth on 1 is 20, number of teeth on 3 is 30. So we can find out what is the number of teeth on gear 4. For that we write pitch circle radius of gear 4. As we see, this is the pitch circle radius, is pitch circle radius of gear 1 RP1 plus diameter, pitch circle diameter of gear 3, that is twice RP3. Because all the gears have the same modules, pitch circle radius is also proportional to the number of teeth. So from here I can write number of teeth on gear 4 is number of teeth on gear 1 plus twice the number of teeth on gear 3. N1 is 20, N3 is 30, so N4 is 80. So that gives me N4 is 80. To consider this gear train, as before we make the tabular method, we write condition and revolutions of gear number 1, 3, 4 and the arm which is nothing but gear 5. So first condition is lock this arm, lock all the elements to this arm, all elements locked to arm. After locking all the elements to the arm, you give y revolution to the arm. Because everything is locked, so we get the same number of revolutions in all the elements. Next, you lock the arm that is arm is locked, no revolution to the arm, and give any revolution x to say 1. If I give x to 1, then 3 rotates in the opposite direction and minus, so it is minus x into n1 by n3. Because this is an external gearing, so they rotate in opposite direction and inversely proportional to the number of teeth. Now rotation of 3 causes rotation of 4, but this is an internal gearing, so they rotate in the same direction. So 3 has a minus sign, so 4 will also have the minus sign, and rotation of 3 n1 by n3 into n3 by n4. As I said earlier, this intermediate gear number of teeth is not relevant, so it cancels. So we get x, I am writing this line again, x, this is minus n1 by n3, so it is 2 by 3 x minus x 20 by 80 is 4 and this is 0. This line I am just repeating. Now let me talk of the resultant motion. You add these two motions. So here I get x plus y. Here I don't need 3 because c is not given, I don't write it. 4 I get y minus x by 4 and arm I get y. Now input speed is given 1000 rpm, which is the speed of 1, that is x plus y. So I get x plus y is 1000. I am taking this direction as my positive direction, as the direction which is shown, which is counterclockwise. So this is the axis. This is the positive direction. So x plus y is 1000 and n4 is 0. So y minus x by 4 is 0, which if I solve these two equations, I can get x equal to 800 and y equal to 200 rpm. And arm 5, which has the speed y, that is speed of arm 5 is 200 rpm. When I analyze this part of the epicyclic gear train, I know the speed of arm 5, which is nothing but 200 rpm. And gear 2, again the speed will be known because that is same as shaft 1. Gear 2 and gear 1 are one compound gear integral to the shaft 1. So in this epicyclic gear train, I will know two speeds. That of speed of 2 is 1000 rpm and speed of 5 is 200 rpm, and I should be able to solve for the speed of the arm, as I will show you just now. Let me now analyze the second epicyclic gear train consisting of gear 2, gear 6, gear 5 and this arm. This arm carries gear 6. Remember, this gear 5 was nothing but the arm of the previous train which I have just now solved. We have already seen that N5 was obtained as 200 rpm and N2 is given as 1000 rpm, and our objective is to find the rpm of this arm, which is the output shaft, which is connected to the output shaft. So gear train is 2, 6, 5 and the arm. So as before, we write condition and revolutions of 2, 6, 5 and arm. First, lock all elements to arm. All these elements are locked to the arm and give y revolution to the arm. So all the elements get y revolution. Then lock the arm that is arm no revolution and give, let me call it y1 so that we do not confuse with x and y we used earlier. Let me call it y1 and lock the arm and give say x1 revolution to gear 2. Then gear 5 rotates in the opposite direction because this intermediate gear makes it opposite direction. 6 and 5 rotate in the same direction. So minus x1 into number of teeth on this gear is not needed. So 24 by 80. So the resultant is x1 plus y1, y1 and y1 minus 3 by 10 x1. So what we see, the speeds given are n2 and n5. n2 is x1 plus y1, which is 1000 n2, and n5, which is y1 minus 3 by 10 x1, and that is equal to 200. And we have to find what is the speed of the arm, n arm, that is output speed, which is nothing but y1. So if you solve for y1 from this, what we get, we eliminate x1, I multiply by 3 by 10 and add, so I get 13 y1 by 10. 3 by 10 I have multiplied and adding, so x1 getting cancelled, 3 by 10 plus 1 give me 13 y1 10, and this is 3 by 10, that is 300. So 300 plus 200 is 500. So y1 is 5000 by 13 rpm. Because it is positive, that means it is in the same direction. So we get the output speed as 5000 by 13 rpm in the same direction. Next we shall solve one more problem involving epicyclic gear train. Let me now solve one more problem of epicyclic gear train, which is shown in this sketch. This gear 1 is mounted on shaft 1, which is rotating at 2000 rpm in the direction shown. The number of teeth on gear 1 is 20. Gear 1 is connected to gear 2, number of teeth on which is 40. Gear 2 and gear 3 forms a compound gear, that means they are the same rigid body, and number of teeth on gear 3 is 30. This shaft 2, which rotates at 350 rpm, carries this arm. This shaft is the arm. As it rotates, this takes these two bevel gears with it. There is a revolute pair here between the arm and these two bevel gears. This bevel gear 3 is connected to bevel gear 4, number of teeth on which is 64. This gear 4 and 5 are compound gear again. They have the same rigid body, and there is a revolute pair between the arm and these two gears, which is the same rigid body 4 and 5, and the number of teeth on 5 is 24. Gear 5 is connected to this bevel gear 6, number of teeth on which is 18, and gear 6 is connected to the output shaft. So these two input speeds are specified, that of the arm and that of gear 1, and we have to find out what is the output speed in 3. The thing to note in this particular gear train is that gear 1 decides the speed of gear 2, because this 20 and 40, so if this rotates at 2000 rpm, gear 2 rotates at 1000 rpm opposite to this, that is in this direction, gear 2. N2 is known. If I take this as my positive direction, then what is given is N arm, I take this direction as positive, N arm is 350 rpm, and N of 2, which is decided by N of 1, which is 2000 here, so that is 1000 rpm opposite to this, that is the same direction as this. And now we can forget about gear 1 and we have an epicyclic gear train. That means this gear 1 is not a part of this epicyclic gear train, which is obvious, because when you arm when you lock all the gears to the arm, I cannot lock this gear, because then this gear cannot rotate. This is mounted here in the bearing, but if I remove this gear from this epicyclic gear train, rest of it is a simple epicyclic gear train. Only thing, speed of 2 is decided by that of speed of 1. That is the only difficult point in this problem. Once we have reached this stage, this epicyclic gear train is simple. So, what it consists of? We can write the same table, revolutions of gears 2 and 3, which is same, then 4 and 5 we are not interested, that is intermediate gear. So, we write gear 6 which is rotating about the same axis like gear 2 and 3, and also the arm which is rotating about this axis. So, we write arm. Then we write condition. First condition, all elements locked to the arm. And if arm is given wide evolution, then 6 gets wide evolution, 2 and 3 also gets wide evolution. We are not writing these two bevel gears, because as you see, the rotation of these gears along with the arm and their rotations about the arm are about different axes. These two gears rotate with respect to the arm about this axis, whereas the arm is rotating about the horizontal axis. So, we cannot add those kinds of things, and we are not interested because these are intermediate gears. So, you do not write it here. Here we write lock the arm is given no revolution, and if I give x revolution to 3, then 4 rotates due to gearing action, which is 30 by 64 into x. If it is rotated in this direction, then it goes in this direction. So, this gear will rotate in opposite direction. These two gears, due to this bevel action, rotates in opposite direction, and their rotation is multiplied by is decided by the number of teeth on this and this, which is minus x into 30 by 64, and these two rotate in the same direction. Then ratio here is rotation of this I get as minus x, not minus, because their rotation is different direction. So, I am not talking of that. 6 is rotating due to this, is 24 by 18. This has 24 teeth and this has 18 teeth, so it is not 24 by 18. This will rotate more, so it is all right, 24 by 18. This is rotating 30 by 64, this is rotating 24 by 18. So, now we get the resultant. So, it is x plus y, and this is y, and this is y minus, if I cancel 18 and 35, and if I cancel 8, 3, 8, 3 and 3 cancels. So, y minus 5x by 8, out of which we are given n arm y is 350 and 2 is 1000, x plus y is 1000. So, we get x equal to 650, and we have to find the revolution of 6, which is N3. So N3, which is same as N6, which is y minus 5x by 8, which is y is 350 minus 5 by 8 into 650. If you calculate this, this is 325 into, this is 4. So 4 into 350 is 1400, and 5 into 325 is minus 625, so it is minus 225 by 4. So if this rotates in this direction, this is minus, so it is in this direction. This is this axis, this is this axis, and the value is 225 by 4, which is 56.25 rpm. So the output speed is 56.25 rpm opposite to this direction. So that is how we solve this epicyclic gear train. Only thing to note that this gear does not belong to the epicyclic gear train, and if we have bevel gears, then we should not write it in this table, because then we cannot add simply like this, because all these rotations are about this axis, whereas bevel gear with the arm rotates about this axis, but their gearing action make them rotate about a different axis. We cannot add rotations about two different axes algebraically. So this is how we solve the problems of epicyclic gear trains. Now that we have explained how to analyze this epicyclic gear trains, so for the kinematics is concerned, that is how to obtain the speeds of different gears. What is the difference between gear train and gearbox? Gearbox, as you know, there is one input speed, but I may require to get various different output speeds, and accordingly we change the gears within the gearbox, the gear engagement we change, and using different set of gears within the same gearbox I can create different output speed, as we do in an automobile. From the same input speed I can go to first gear, second gear, third gear, as you want to increase the speed of the car. But there are two kinds of gearboxes. One is where the gears are changed, that is the output speed is changed after bringing the entire system to rest. We change the gear engagement within the gearbox by sliding or something, and then get a switch on the machine and get a different output speed, as we do in case of a machine tool. The motor of the lathe machine rotates at a constant speed, but I want to get different output speed at the headstock, or I want to rotate the job of the machine at different speeds depending on the diameter of the job. So in machine tools we use a kind of gearbox where we bring the entire system to rest, change the gear engagement, and then again switch on the machine. Whereas in automobile we need to change the gears while the car is in motion or the input motion is on. We cannot switch off the car and then change the gears. We have to change the gear while it is in motion. For that, these gearboxes are more complicated, and we have to use what is known as synchromesh. This is a complicated system where a clutch action is needed such that gears which are going to engage are speeded up and get into the same speed before they proper speed before they get into engagement. Whereas these machine tool gearboxes, which are easier to design and easier to analyze, uses what is known as sliding clusters. We shall end this course by having a little discussion on this sliding sliding cluster gearboxes which are used in machine tools. That is, from one input speed I want to get several output speeds by changing the gear engagement. I will show you through figures now such a sliding gearbox which are used in machine tools. This picture shows what I just now said is a sliding cluster gearbox which are used in machine tool application. This is the input shaft and this is the output shaft. For the same speed of the input shaft omega I may like to get 3 different output speed omega O. To do that, I have a compound gear. This is the same rigid body, and this whole cluster can be moved along this shaft. This shaft is a spline shaft, and on this spline shaft this whole cluster can be moved. Right now this gear B is in engagement with this gear E, so it transmits a particular speed ratio. If I want a different speed ratio, I stop the entire machine, then slide this cluster such that this gear C comes in engagement with this gear F, and depending on the number of teeth they will transmit a different output. Again, if I want to have a different another third different speed, I will stop the machine and move this entire cluster such that this gear comes in contact with this, engagement with this, and depending on their number of teeth they will transmit a particular speed. So this is a 3-speed gearbox using 6 gears, and this is the sliding cluster. This is one rigid body, but number of teeth are different on these 3 gear bodies A, B and C. The thing to note is that before this gear comes in engagement with this gear, the gear which was already in engagement must be totally clear. It must leave this engagement before it starts engagement. Similarly, when I move it this way, before this gear comes in engagement with this gear, this engagement must be fully clear. So if suppose the gear phase switch of all these gears are same and I call it B, if every gear the width is B, then this total distance as we see is B plus B, because if it has to clear, that movement is B, so before it comes into engagement, so B plus B plus B plus B plus B, again this gap must be B and B, so this whole distance becomes at least 7B. So it should be more than 7B. One more thing to note is that the number of teeth difference, the difference in the number of teeth between these 2 gears must be at least 4. Otherwise, while moving in this direction, this gear will foul with this gear. As we see, pitch circle radius of this gear B plus pitch circle radius of this gear RE, that is the center distance. But when this gear is sliding over this, this must be greater than the outer radius, sum of the outer radius of A and B, otherwise A will interfere with E. The outer radius of A plus outer radius of E, the center distance should be more than that, such that this should not interfere with this when I am sliding it to the right. Now if you remember, the outer radius is pitch circle radius plus the module. So outer radius is pitch circle radius plus the module. So if I cancel pitch circle radius of this, so pitch circle radius of B must be greater than pitch circle radius of A plus 2m. And if you remember, the number of teeth module is nothing but number of teeth pitch circle diameter by number of teeth. This is the module. So RB, I can write module into number of teeth on gear B divided by 2 should be greater than module into number of teeth on gear A divided by 2 plus 2m, where m is the module. So if you cancel m, I get NB should be greater than NA plus 4. So for designing such sliding cluster gearboxes, one has to ensure that the minimum number of teeth between these two adjacent gears on a cluster is at least 4. It should be more than 4, and this width should be sufficient such that total disengagement takes place from this pair before the other pair this way or that way comes into engagement. Using the same thing, I can get a 9-speed gearbox. If this is the input shaft and this is the output shaft, and this intermediate shaft I make it spline, and here I keep 2 sliding clusters. So depending on where the connection is taking place, I can get from the same input speed 9 different speeds. For example, right now this and this is in engagement, and this is in engagement. So depending on the number of teeth on these 4 gears, I get a particular output speed. Now if I change it, slide it, this comes out of engagement and this becomes in engagement, and here it is the same. So depending on the number of teeth on these 2 gears, I get a different speed. So that way I can get 3 here and 3 here, and by combining them 3 into 3, I can get 9 different output speed from the same input speed. This is what is called sliding clusters gearbox, which are used in machine tools. This is a 9-speed gearbox. From the same input speed, I can get 9 different output speeds. The thing to note that because spline shafts are much more costly, we have put both the sliding clusters on the same shaft. Input shaft, intermediate shaft, which is the spline shaft, and this is the output shaft. Input and output shaft have fixed gears, whereas this intermediate shaft, which is a spline shaft, has sliding gears. So this is a sketch of a 9-speed sliding cluster gearbox. But as I said, for when the gear change has to take place while the whole system is running, that is much more difficult to design, and we need what I call synchro mesh, and that is beyond the scope of this course.